Did that make sense? I think we can try this on a far more complex problem. This one is actually from the 2021 AME 2, problem 8 specifically. So, imagine that there is an ant on a cube. This is actually kind of a trope when it comes to math problems. I swear on math competitions, there's always at least one problem that discusses ants on cubes. I don't know why. The ant starts on any one of the vertices on the bottom face. After that, the ant moves randomly to any of the other 3 edges. Note the ant can only walk on edges, not on faces, just on edges. And suppose an ant goes from here to here. The ant can't immediately just go back. The ant can't go backwards and retrace its path. So the answer is, after 8 moves, what is the probability that the ant is on a top face? It's tempting to immediately say 1/2. There are 8 vertices and 4 on the top. 4 divided by 8, it was 1/2. But no, it's not actually that simple, sadly, because we have to consider the fact that the ant started on a bottom face, and that actually affects the probability a little. It might be tempting to get out the probability tree. Okay, we'll try that. The ant starts from bottom face. Of the 3 vertices it could go to, 2 are on the bottom and 1 is on the top. So it has a 2/3 probability of staying on the bottom face and a 1/3 probability that it goes to the top. And then we can continue drawing out the probability tree. The issue is we have 8 moves, and this is only the first move. Here we have 2 branches, and seeing as each branch branches out into 2 other branches, we might have, let's say, about 64 branches. Well, in reality, that's not the case. Some branches terminate, but still, way too many branches, way too much effort, not worth it. So instead, we do this a little differently. We have to classify the moves. First, let's classify the move B to B. An ant moves from a bottom vertex to a bottom vertex. A move B to T. An ant moves from a bottom vertex to a top vertex. A move T to B. An ant moves from a top vertex to a bottom vertex. And a move T to T. An ant moves from a top vertex to a top vertex. Let's make these all functions of n being the number of moves. This is going to be the amount of B to B moves. This is going to be the probability of a B to B move when you have n moves. This is going to be the probability of a B to T move, a probability of a T to B move, the probability of a T to T move. Is this making sense so far? I really hope it's making sense. Anyways, after that, so now we just need to define all of these, right? Well, let's do a little bit of thinking. If we go from B to B, then what's the probability that comes afterwards? After you go from B to B, you could either go to T or to B. Both of these occur with a probability of 1/2, right? Because one of the bottom vertices has already been taken up. So there's 1 left for bottom and 1 left for top. So that means of B to B, 1/2 of B to B sort of goes to B to T. The other half goes to B to B, if that makes sense. I know I say that too much, but still. So we can say that 1/2 of b to b n minus 1 goes here. 1/2 of b to b n minus 1 goes here. Now let's think about b to t. This could go to b, or it could go to t. But b to t to b is impossible, right? Because if an ant on the bottom vertex went to the top vertex and then immediately went down to the bottom vertex, it would have to retrace its path because there's only one possible face-changing vertex, face-changing move, right? So this is actually impossible. It is certain that all of b to t leads to t to t. So we're just going to put all of b to t over here. Now let's think about t to b. We can see that the situation for t to b is actually pretty similar to the situation from b to t. Going to t to b to t is impossible, so that happens with probability 0. It happens with probability 1 that it goes to a b to b situation. So here we can add plus t to b minus 1. Note, in case this is hard to read, it says b to b of n is equal to 1/2 b to b n minus 1 plus t to b n minus 1. Because all of t to b n minus 1 has to feed into the b to b stream. Now let's discuss t to t. Here, 1/2 of it could go to t to b, the other half of it could go to t to t. I'll move this eraser so you can see. We can add that accordingly. Even though it may sound really different from what we did in the last problem, the basic idea is the same. We're dividing these into cases and then using that to find a recursive formula by seeing which moves are possible after an ant takes a certain move. So now we have 4 recursive formulas. Note that we want the probability that the ant ends up on a top vertex. So we want the sum of b to t of 8 and t to t of 8. Now all we need to do is get a recursion table going. To do this, I will unfortunately have to erase this cube, and then I can draw a table. B to b, b to t, t to b, t to t. Note that the ant starts on b. So at the first move, b to b happens with a probability of 2/3. b to t happens with a probability of 1/3. t to b and t to t are impossible because we started on b. Now after the second move, what's the case? b to b of 2 is going to be equal to 1/2 of b to b n minus 1 plus t to b n minus 1. So this is going to be 1/3, calculating using this formula. b to t is going to be equal to 1/2 b to b n minus 1, 1/3. t to b is going to be 1/2 of t to t, but t to t over here is 0, so this is also going to be 0. t to t of 2 is going to be equal to b to t n minus 1 plus 1/2 of t to t n minus 1. But this is 0 and this is 1/3, so this is also going to be 1/3. Note as a quick check, all of these probabilities must add up to 1 on each row, because these are the only possible cases. So if it's not adding up to 1, then you've done something wrong. Now, I'm just going to go quickly fill this out, and I will spare you having to watch me do it.